we will talk about benchmarking safety monitors for image classifiers with machine learning. So just a quick introduction. We are talking about image classifier with machine learning, more specific deep learning techniques like deep learning algorithms like deep neural networks, for example, convolutional neural networks. And for this kind of machine learning models, we have a common issue that is even though these machine learning models can be very accurate, we have the problem that sometimes these models, they out predictions, wrong predictions, even with 100% of confidence. And for cybercritical systems like autonomous systems, autonomous vehicles, for example, this can be a very important problem. So for this kind of issue, we usually apply some dependability ensuring techniques, and we have a lot of things actually. But one category of dependability techniques is the fault tolerance that's applied mainly to increase the safety regarding the functioning of these systems, but at runtime. So instead of developing something to catch some errors in the system before to put in production, we assume that all possibilities have been done to find problems during the development of the system, and we assume that okay, you have done everything that you could do, but now we will apply something to inspect the correct functioning of these systems during runtime, during operation. And one of these techniques is called safety monitor. It's like a redundant software that goes to along with the system that you want to inspect at runtime, and it can give you some guarantees that the system will operate in a safe state despite hazardous situations like the error of the machine learning in this case. And such safety monitors that we are applying here to these image classifiers, they are intended to detect out of distribution images at runtime, because are these images that are dangerous to the correct function of the machine learning, since the machine learning is trained normally over the assumption that the data is independently and identically distributed. What means that it is expecting that the machine learning model was trained in a training set that is representative of the data that this algorithm will find at runtime. And for out of distribution data, we are considering 5 types of out of distribution data. And the first one, for example, is noise. As you can see, for example, is some errors in sensors that can yield this kind of problem. We have distributional shifts, that is when the distribution of the pixels are changing because of environmental conditions, or because of other factors like light or light conditions or other kinds of transformations that the image can suffer at runtime. Novel classes that are new classes that your machine learning doesn't see yet during training. Anomalies, in this case, even though we have a lot of different definitions for anomaly, we are considering here anomaly as something that you cannot consider the image to do any prediction because of also because of sensor errors and adversarial inputs that in this case can be handcrafted to fool your machine learning model. And recent works to safety monitoring these problems, these issues, this out-of-distribution data, they have been proposed in the literature, and we call here data-based safety monitors, because these safety monitors are built using usually the same training data set, or at least observing the training data set that the machine learning was using. So these database machine learning monitors, or these database safety monitors, they can be applied in 3 different ways. The first one is observing, monitoring the inputs of the deep learning model, in this case, images, or observing the intermediate layers of the deep learning model, for example, activation functions coming from the ReLU, for example, or observing the decision of the machine learning model. In this case, the class predicted along with its contents. But the confidence on such safety monitors based on data, it's a kind of open issue, because it's quite difficult to understand if these safety monitors don't suffer from the same problems that machine learning suffer, that is being biased to the data and doesn't have any model of the system, because it's quite difficult to reversing a machine learning model, especially big architectures, and the properties is quite difficult to define as well. And we have a lot of parameters inside of a machine learning model that are non-linearly correlated. And another important thing is that despite we have at least 2 related works for benchmarking safety monitors, for machine learning at runtime, our work differs from these 2 in 3 different aspects. So the first one is that we propose a framework that covers the entire pipeline, data generation, testing, and evaluation. The second thing is that we apply metrics beyond the traditional accuracy and other kind of curves based on false positives and false negatives. And we apply also a statistical analysis. And we test 5 different types of OOD data. And the amount of data sets that we apply in benchmark is quite bigger than the other related works. So this is the high level, the picture of the high level picture of the architecture, and it's quite simple actually to understand. So the first one is data profile, where we generate the benchmark data sets using the original data set that used to train machine learning, and apply a fault template to make the transformations on these data sets. The second module is the model that we wanted to perform the test on the system. So here we use a machine learning model and a safety monitor. And the data set containing these transformed images, they are applied in inside of this module. And in the end, we have the outputs of this test, and we evaluate these outputs to give some analysis. And for example, for a data profile, we applied as the in-distribution data set, we applied the German tribe sign containing 43 classes, the Belgian tribe sign containing 62 classes, and Cipher10 containing 10 classes. And we applied the full template that contains 5 types of OOD data. And in the end, we produced 79 benchmark data sets. And of course, we don't use the transformed data to train the machine learning, neither to make assumptions to the safety monitor as well. And in this data benchmark data set, they are composed of 20% of in-distribution data. That is the test data in a normal scenario of machine learning, and the entire original data set, but transformed with our fault template. And the system under test is composed, as I mentioned, with the safety monitor and machine learning. We give an incoming image both to the machine learning model to give a prediction and to the safety monitor to detect if it's out of distribution data. So this produces 2 kinds of outputs. The first one is specific to the OOD detection, and the second one is regarding the overall performance of the system. It means that when the machine learning receives an image and gives a prediction, we look at the safety monitor answering that is out of distribution data detected. And if the safety monitor says that is out of distribution data, it cancels the machine learning decision, because the machine learning model cannot be trusted with an image that is out of the distribution that he was trained before. We also measure other general readouts like processing time and memory usage. So the evaluation, as I mentioned, we have the performance of the safety monitors regarding the detection. We have the overall impact of the safety monitors on this system, because something that's quite important is to know why, how the safety monitor is impacting the machine learning performance. And time and memory overhead induced by the safety monitors, because we are talking about solutions that can be used at runtime in safety critical systems like autonomous vehicles, and the time and processing time and memory overhead is quite important. And we apply 7 metrics. Instead of accuracy, we apply Matthews correlation coefficient that is way more accurate, especially for imbalanced data sets. And it varies from -1 to 1, where -1 is perfect inverted accuracy. And 0 means that's near from the random classifier, like tossing a coin. And the value of 1 means the perfect accuracy, when the system being tested give right answers every time. We have false positive, false negative, precision recall, micro F1, that's a metric to see how this performance is given in over classes. And we have the critical difference diagram, that is a statistical analysis to see if the safety monitors are really different from each other regarding the detection performance. So here I put just one table that is regarding the parameters that we use it in the 3 methods that we tested as a safety monitor. The first one is the first method that we applied for safety monitoring is a method based on observing the DNA inputs, the images. This method just try to reconstruct an image at runtime to an image that he knows from the training set. And if the error in this reconstruction is too high, it means that it's a new class, for example. We have the second approach that is called outside of the box, and it looks at the intermediate values of the neurons network, the neurons of the neural network. For example, just record the activation functions during training of the neural network, and it builds some patterns like a box, a 2D box, and during runtime it takes the image, an income image, look at the activation function of the neural network when giving a prediction to this image, and this method constructs a point, and this point, this method tried to look at this point inside of this database of 2D boxes. So if the point falls inside of this 2D box regarding a specific class, so it's okay. Otherwise, if it falls outside, it means that it's a new class. And we have Odin that's based on the decision. Actually, it's based on the confidence values of the decision. It's just try to rescale these confidence values to be something less overconfident regarding the prediction. And here, this table, as I mentioned, is a table with some parameters that we tested. Actually, I tested all the parameters that the original papers tested too. And we applied other parameters as well to be tested beyond the ones that were tested on their original papers. And here I put just a table regarding one type of OOD data. In this case, it's Nogat class. And we have a German traffic sign in Belgian traffic sign, cipher 10 in German traffic sign in cipher 10. In this case, here it means ID dataset and OOD dataset. And despite we have sometimes a good value for the F1 metric, it's based on false positives and false negatives. We have the constatation that the MCC value is quite low. So it means that the performance to detect out of distribution data here is near to the random classifier. And we applied a Friedman test to build this this score here, just to show that when we tested all these safety monitors through all the data sets and all the types of OOD data, in the end, even though Odin achieved the first place or the best performance between the 3 methods, in fact, they don't have any difference if we consider statistically these results. So it means that all the safety monitors didn't perform it well, and we don't have actually a safety monitor that is better than the others, at least for between these 3 state-of-the-art methods. And regarding the impacts of the safety monitoring system, when you apply just the machine learning alone, of course, it's quite performant, but when you apply these safety monitors, because of the amount of false positives, the performance of the system decreases. Of course, that we don't expect that the safety monitors will perform better than the machine learning. Otherwise, you could use just the safety monitor to do the task. But we see a huge decrease in the performance. MCC from 1 falling to 0.5. In the case of outside of box, 0.6. Okay, but is still a huge gap. So it's quite difficult to rely on the safety monitor when you know that the safety monitor is decreasing the default performance of the system. We have the time and memory here overhead. As you can see in the first table, the monitor is quite, we can see that it's quite fast, but is responsible for more than 90% of the overhead of the system. So it applies actually a lot of overhead inside of the full system. And we have in the second table, the memory usage from these safety monitors. They are not expensive, except the one that's based on a neural network model that is a lock, that is training one class classification for, is trained for one class. And we have, for example, in the case of German traffic sign, we have 43 classes. So you have this problem that even though it's just 2 megabytes per class, when you apply for 43 classes, we have almost 100 megabytes of memory being used. So just to finish, some conclusions is that there is a need for a better benchmark framework for database safety monitors, because we found that this benchmark yielded worse results than the other benchmarks, especially because we applied some metrics that yields this. And normally is the papers that propose safety monitors, they just look at the, they normally look at the performance of the safety monitor to detect out of distribution data. But when you detect out of distribution data, what do you do? So if you say that you don't consider this image to be the machine learning, to be feed the machine learning model, it means that you cancel, probably you cancel the answer of the machine learning model. So if you do that, the performance is quite, there's a huge impact on the safety, on the system under test. So we have to at least to consider 2 dimensions when you frame, when you benchmark these safety monitors. And some limitations of this work, we have some limitations that, for example, we didn't apply more in bigger DNA architectures. We applied just for convolutional neural networks with 128 layers, for example, in the last hidden layer, 128 neurons in the last hidden layer. And we benchmarked just over image data sets, but we didn't consider the entire system. We consider just this small component that is giving a prediction and look at the safety monitor decision. And we didn't apply any type of centered quantification methods inside of this framework. So the general takeaways, database safety monitors don't provide sufficient confidence for using in a safety critical application. A lot of false positives or false negatives depend on the auto distribution data. They affect negatively the system they test. They use a very near approach from the machine learning, and it considers a lot of memory sometimes, and it induces a lot of overhead in the system as well. And the specific takeaway is that safety monitors based on DNN inputs are good to inspect the internals. Doesn't need to inspect the internals of the DNN, what's something good. So you can apply black box machine learning models, but it's quite biased to the data that you have. And safety monitor for DNN intermediate values is good because you can look at the machine learning model and try to figure out what this machine learning model is doing. But the problem is that, for example, if you use activation functions to do that, they don't provide all the information learned from the DNN, except when you can look at all the activation functions. But if you try to figure it out how these activation functions are linked to each other, and you can figure out the nonlinear relation and relationship between then all these things, it's quite near from what the machine learning model is already doing. And you have the safety monitor based on DNN outputs. That is interesting because you can rescale the confidence values of the DNN. So it means that you don't need to consider to look at the DNN internals, but again, it relies a lot on the performance of the DNN. So the DNN has not a good performance over this OLD data. It means that you are rescaling confidence values of something that's not giving you a good answer already. So here the reference, and thank you for your time.